Hello. Hello. Today's video is about Navier-Stokes equation on usage of computational fluid dynamics. So this is finally a subject. So Navier-Stokes equation is one of the important equations for computational fluid dynamics because it includes shear stress and various stresses about how this viscous forces are calculated. So derivation of this equation starts with creating a body in three-dimensional body. So starting with the Euler's equation, so it includes tangential stress uh, in x direction, y direction, and z direction. Tx, Ty, Tz be the components of shear force per unit mass in x direction, y direction, and z direction. So the need of x direction, y direction, z direction is that the shear stress which is acting on the x direction will have an impact on y direction and also in z direction. Similarly, all shear forces will have an impact on all other directions. Having faces, that is A, B, C, D, E, F, G, H. So these are forces in the AEHD direction, that is kinematic viscosity into du, dz, dy, dx. Similarly for all directions, that is BE, GSE, then AEHD, BFC. So we added, so because we are calculating only for the x direction. Similarly, for the excambient resistance forces on the other direction, that is EFGH, U dx dy du by dz, excambient forces on the ABCD phase, that is U into mu into dy dz, dou u by dou x plus dou squared by u by dou x squared dz. The net excomponent of resistance forces on the phase EFGH ABCD are mu into dou squared u by dou x squared dx dy, and similarly, for the HGD and EFB bases are dou squared u by dou x squared dx dy dz. The total viscous force resistance are calculated for all the directions, that is in the x direction. So when you remove the common terms, you will get this equation, that is mu into dou squared u by dou x squared plus dou squared u by dou x squared dou squared u by dou z squared dx dy. The analogous equation for the components dy tz are this one, these things. Then for the dx direction, when you bring everything into in this equation, you get this equation. So for the x direction, so we are calculating only for the x direction, dividing the equation throughout divided by p into dx dy and dz, we get, so this is your x direction, 1 by rho dp by dx du by dt v into dou squared u by dou x squared dou squared u by dou u squared dou squared u by d. So this is pressure term, so this helps us to calculate what is the pressure which is acting on the fluid element. So this is acceleration due to gravity of the fluid element. So this is the velocity variation in the all directions. So the mu represents the kinematic viscosity and density of the. Similarly, we can calculate it for the y direction, z direction. So the application of Navier-Stokes equations are vast. So it is applied mainly in calculating the flow velocity around an objects, and also in the inside the objects, mainly used for external aerodynamics in terms of proportion, also how the fuel is mixing with the air. So the Navier-Stokes equation helps us to calculate and able to create a mathematical modeling for calculating the turbulence velocities also. So this Navier-Stokes equation leads to the turbulence modeling also. Thank you. Then applications, as I said, the laminar flow in the circular pipes, laminar flow, unidirectional flow between the stationary parallel plates, laminar unidirectional between the parallel plates, laminar flow between the concentric rotating cylinders. Okay, so these are the basic applications in things. So here the laminar flow is there. Navier-Stokes equations at the preliminary stage, it is mainly used for integrating flows is in the laminar flow. But when you calculate all the stresses in all directions, these still leads to the Reynolds stresses. The Reynolds stresses will help us to calculate the stresses in all directions of x, y, z and their impacts. This leads to the formulation of and mathematical modeling of a turbulence flow. Thank you.